Okay, I think let's start with the session. So, good afternoon, everyone. Dear authors and all the invited guests, a very warm welcome to Technical Session 9A. Myself, Yashita, and I'll be your moderator for this session. I'll make sure that everything runs smoothly and maybe try to keep up the energy too. So, on behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you all to the 11th International Conference on Information and Communications Technology for Sustainable Development, which is ICT4SD 2026 Goa. So, the 11th edition of the conference is being held in a hybrid mode. The physical event was held yesterday on 9th July in Goa, and the virtual event is being held through Zoom from 9th to 11th July, where people from all over India as well as many from other countries are present with us. So I hope that you all enjoy today's insightful and knowledgeable sessions. So in this session, we will be having a total of 10 presentations. Each presenter will be given 10 minutes for presentation, followed by a 2 minutes for question and answers. And I will be giving a gentle reminder at the 8-minute mark just to stay everyone on track. Also, small request to all participants. Please stay connected with us till the closing remarks. We promise that the session will be worth it. And if you have any queries or updates to tell, feel free to drop them in the chat box anytime. Me and my co-host will be addressing them. So before we begin, I would like to introduce you all to our esteemed session chair. We have with us Dr. Kirti Vanzale ma'am, who is an assistant professor at VIT. Who is an professor at Vishwakarma Institute of Technology, Pune, with over 22 plus years of distinguished experience in engineering education. She manages high impact academic quality frameworks alongside active research portfolios in emerging computing architectures. Her expertise focus on wireless sensor networks, artificial intelligence models, IoT applications, and computational image processing. So, welcome to the session, Kirti ma'am. Do you have something to say to start the session? Okay, I think we should move forward with the next presentation. So, our first presenter for today is Shimona Sinha. Shimona, are you present in the meeting?
Yes, ma'am. Yes, ma'am.
Yes.
I'll,
Yes, so she is here to
I'll.
present her paper titled as a resilience as a service approach for cloud IoT using SORRIR middleware. So yes, Shimona, you can start presenting.
One second, yes.
And a reminder to everyone that you have to wrap up your presentation within 8 to 9 minutes as we are time bounded, and make the session as interactive as possible as we are connected online. So anyone can ask questions.
Ma'am, can you
So
see my screen?
yes, it is visible. You can start.
Good afternoon, everyone. I'm Shamona Sinha, and my co-authors are Rucha Vikrant Vadwakar and Jenny Jito, ma'am. So, we have Rucha along with us today. So, I'll be presenting our work, that is resilience as a service for cloud IoT. So as a service for cloud IoT. Basically, and we are from Department of Computer Science at PES University, Bangalore. So just to give an introduction to it, resilience as a service is basically a pluggable middleware layer that lets IoT cloud systems detect and recover from fault automatically. So it basically combining anomaly detection, edge level recovery, and cloud level consensus into one particular system, so one unified system. So build on the Sawyer middleware, it just cuts the response time by 98% and eliminates the downtime compared to existing approach like Carol. So we have the problem if you just worked with platforms like AWS IoT or Azure IoT. You just know that they're excellent at monitoring. They'll just tell you a device went offline, or a sensor is reporting bad data, or latency spiked. So but here's the gap: monitoring tells you something is wrong, it doesn't fix it. Recovery is still reactive and human driven. Someone has to look at the alert, diagnose it, and just manually step in. So at the scale, the this becomes the bottleneck, obviously. So higher operational overhead, lower response. Then because of edge and cloud layer often operate in isolation, so a fault can spread before anyone can even react. So what is exactly existing? So what's been already tried? So Sawyer middleware, so first is our Sawyer middleware, which is the core of our project. So Sawyer middleware separates the resilience logic from the application logic, great foundation, but on its own it has no built-in anomaly detection. Next up we have the Carol, the closest prior work to ours, handles broker for worker failure well, but that is also a limit. It just doesn't generalize beyond that. Then we have the right protocols, as you can see. It solves the network layer rerouting, but doesn't touch device level or compute level faults. So each of these solves a slice of the problem, but none of it solves, just covers the whole picture. So we will go, that's where our approach comes in, basically. So we call it resilience as a service. The core idea is basically the separation of concerns. Resilience logic lives outside the application, so recovery behavior can change without even touching application code. We just split it into two edge and cloud layers. At the edge layer we have the lightweight RAS agent, which is basically to fix faults close to the device, that is restart, rollback, or reroute with minimum latency and minimal dependency on the cloud. And at the cloud layer we basically handle what the edge cannot, so multi-node failures or global state synchronization, etc. Now we'll just go through, just let me just walk you through the architecture. So the device first feeds into the ML based detection using the isolation forest, which connects into the Sawyer middleware, our policy and state engine, and from it it connects to the network layer, which is the write C write D, and then to the RAS agent, and then everything is like shown it into visualized on a dashboard, basically. So the Sawyer bridge then connects the edge to the cloud layer, where the AWS is basically computed, the BFT recovery orchestrator is there, and Prometheus for just operating and monitoring. So the flow is like, if something is like, the flow is detected at the edge, it tries to recover at the edge and only escalates to the cloud if genuinely the edge cannot help it. And we also have the application layer, that is the Docker. Next step is the pipeline, the detection and recovery. So for detection we have used isolation forest and unsupervised detection algorithm, so we don't need labeled for data in advance, obviously, and it's fast enough to run directly on resource constrained edge devices. And then once fault is flagged, the RAS agent is there, which basically tracks matrix locally and on the threshold breach, restarts or roll back or ride at the edge. No round trip to the cloud. For the network specification, we have two things, that is ride in two phases, write C and write D. Write C consistently, like constantly monitors the latency and whatever links are available, and just keeps the collection of the good parts. And write D basically triggers when the failure hits, the right D triggers, the traffic switches instantly to the predefined paths, which is already collected by the right C. Next up is the Sawyer. Obviously, I've already explained the Sawyer is basically the safe orchestration, resilient, and robust IoT runtime, which is the backbone of our system. We have the states, finite state, standard, degraded, fail. When it goes to degraded, obviously it can roll back, it can revert back to standard, but once failed, obviously it can't. So I just want to explain this. So yeah, the system moves between these automatically as faults are detected. The whole purpose is basically separating the resilience logic from application, so keeping the core logic of the system uninterrupted even if any fault occurs. So that is what the we have used. So we've used the Sawyer as the foundation and built our detection and recovery mechanism on top of it, basically. So next up, obviously the cloud recovery. So now what if a fault is too large at the edge to fix alone? So that's when our cloud layer comes in. Using a BFT, that is Byzantine fault tolerance approach, the system can tolerate up to F faulty or misbehaving nodes out of 3 F plus 1 total and still reach correct consensus. This gets triggered by things like conflicting sensor data or delayed acknowledgement that the edge cannot resolve on its own. The cloud orchestration just verifies basically all the active nodes before resolving the actual issue. So yeah, this is about BFT. And then we have the results. So results, we basically have compared the Sawyer with the base model, which is Carol. So it response time have improved by 98%. The decision time is basically there by improved by 88.7, and energy consumption is reduced, dropped by 78.9, and memory usage also 73.4. So we saw a near to zero downtime with zero retraining needed at all. Next is the evaluation and setup. For that, we've used the ifog sim simulation, and so ifog sim just lets us generate a realistic device, realistic device behavior and inject specific repeatable type fault types, system crashes or performance slowdown, etc. We have different devices like soil sensor, camera, etc., which we have used, and in total we've processed over like 1800 data points for this project. So the key contributions which we have done, to summarize our contribution roughly, we have like 50, we roughly a 50x response time improvement is there, 5x energy efficiency, near to zero time down time operations, and we validate this through across multiple devices and multiple fault scenarios, not just one narrow case. So yeah, to conclude, this resilience as a service just takes fault recovery out of category of something engineers hand built separately for every system. It turns it into a decoupled automatic plug and play layer that just works across both edge and cloud. For future work, we're just looking for maybe an S3 based network simulations, which is more realistic sort of evaluation, or hybrid edge cloud anomaly prediction models. So yeah, thank you so much.
Okay, thank you so much, Shimona. Kirti ma'am, do you have something to say?
Yes, Shimona, you said that your response time has been increased by 50x or something. So, to which devices you are compared?
Carol, ma'am.
Carol.
Yes, Carol is a baseline model which already existed, but with very limited. So we just compared it with that.
Okay, okay. Because you said na you have compared with multiple devices. So, I just
Ma'am,
want to
we've
know.
used
Yes.
no, ma'am, we have used multiple devices, but we have compared our model with only one, that is Carol.
Okay. Okay. Thank you.
Thank you.
Okay, so moving ahead with our next presentation. So we have Sandhya. Sandhya ma'am, are you present in the session? Or any of her co-authors is present on behalf of her?
I'm Siddharth. I'll be taking care of the presentation today.
Okay, sure. So he's going to speak on his work titled as Adaptive Image Enhancement with Reinforcement Learning, a comprehensive survey with the prototype. So you can start, Siddharth.
Thank you. Is my screen visible?
Yes, it is visible.
Okay. Good afternoon, everyone. Today I'll be presenting our paper titled Adaptive Image Enhancement with Reinforcement Learning, a comprehensive survey with a prototype. And to give some information about our team. We are a team of 3 people consisting of our professor, Dr. N. Sandhya, me, Siddharth Verma, and my friend Chandratya Janaswamy. We are from VNR, Nanjoti Institute of Engineering and Technology in Hyderabad, from the Computer Science and Engineering, AML and IoT department. And so let us first talk about the main problem that we're trying to solve. In today's scenarios where AI is being used in almost every domain, uh, computer vision is a new and computer vision is also another field of artificial intelligence, which is being used in various scenarios such as autonomous driving, surveillance, remote sensing, and so on. And in this scenario, we intend to tackle a very real real world problem of image dehazing. Basically, when we are operating in scenarios where visibility is affected by artifacts created by degraded weather, carrying out day-to-day tasks can become difficult, and we intend to solve that problem by creating deep learning based models to process this footage, this video in live, and remove the smoke and haze present in the video and output a much more clearer output so that people can carry on their activities with ease. And for this, this is a fairly research topic in the research topic, and currently people are using different kind of transformer based methods to tackle this problem, such as stance weather, DS former, restormer, and many other methods. But one problem that we were able to identify is that all of these models had one crucial limitation, that they were bounded by the data that they were trained on. For example, if we trained a transformer based model on a data set of, let us say, images of only Ladakh region, then it would not be able to effectively dehaze the images from, let's say, an environment in China, because it simply doesn't have the, it was not able to learn the exact details of what kind of distortions are being created because of the weather, because weather is always dynamic. There is no single type of noise that we can identify and clear out. This poses a problem of that when we are trying to explore or going to new areas, we won't be able to use these algorithms, as they will always be affected by whether we have already have data of that place or not. To tackle this problem, we have introduced the concept of reinforcement learning, which will be able to dynamically adapt based on the input that we are processing. And this current research paper is primarily a literature survey of the various methods used by people to tackle this problem. And we are the papers which we have studied can be mainly classified into 2 types. First, of the baseline models of transformers, which people are using, which give a state-of-the-art performance, which with high PSNR and SSM values. And on the other end, we have also studied some papers which exclusively explore the use of reinforcement learning for such applications to introduce adaptivity. And the main reason why reinforcement learning will be able to work so good is because of its adaptive nature, and we'll be able to uh, make turn enhancement into a closed loop decision making process. And let us look at the taxonomy of our work. First of all, we have discussed about transformer-based backbones such as trans, weather, transformer, prompt DS former. All of these are transformer-based methods. These have been published in the past 4 years, approximately all of them, and they all have introduced novelty. Like some have introduced self-attention. Restormer tried to reduce the computational complexity by introducing channel-wise self-attention, and so on. All of these methods are really good. They give really good performance improvements, but they cannot be used in real world scenarios uh, because of the way that they are inherently. They cannot be adaptive, and this is a huge problem that we have. And then we explored some RL papers, and we were able to find out that RL is being implemented mainly through 4 different ways, such as pixel-wise RL, where reinforcement learning uh, is being used to train an agent which uh, manually changes the pixel values of in each and every image, and it is very computationally expensive. And then we have perceptual and aesthetic RL, which again, instead of focusing on each and individual pixel value in an image, it concentrates on the overall perceptualness of the image using bigger blocks. And then task aware and domain RL perform reinforcement learning by introducing downstream evaluation metrics into the reward loop. Like for example, if your final objective is to identify reject objects in an email in an image, then the mean average precision is also being used in the reward agent to train the RL agent. And then we have even more hybrid and advanced RL techniques which introduce concepts of diffusion as well. And these are basically the small list of the papers which we studied in the literature survey. And let us talk about the data sets. These are some of the most commonly used data sets. For example, the set data set is largely used for testing in image dehazing scenarios, and it is a paired data set. And by paired, I means that for every dehazed image, we have an equivalent clean and ground truth image as well, so that we can compare and both two sincerely. And then we also have challenge data sets such as NHAs and NCAs. These have natural haze present in the images, and these are really difficult to dehaze effectively. We also have other data sets such as Rain 100L and Rain 100H for the specific task of deraining, and Hockey Cityscapes was a dataset built upon NYU Cityscapes just to test how smoothly can we perform object detection on a camera present on top of a vehicle, which has and they have added synthetic fog into it. And low light images was again more towards a night vision enhancement. And why the field is still stuck, and one of the main problems that we found here was that in order for training an RL agent, we need to give it some reward. But another problem that we have is that in order to make a reward, we need to have something from which we can compare the image. Like, this is a good image, we want to move in this direction. But it is not possible all the times to have paid data sets. For example, in real-time scenarios, if we are capturing footage through a camera, we won't have its equivalent ground truth image. So we cannot compare it. So this led to the usage of NRIQA metrics, non-reference image quality assessment metrics, such as BRISC, LPIPS, and music. They weren't meant for specifically analyzing weather degraded inputs, but they were the ones which were being primarily used in such RL agents. But they had a huge problem in them that instead of the RL agent trying to dehaze the image, they were finding other mathematical workarounds to just improve the metrics without much improvement happening in the actual image. So the agent is feel like it's learning something and the metrics are going up, but perceptually we see no improvement. And another weak point that we found was that no one had strongly explored the concept of combining a strong backbone model like a transformer or diffusion based model and then apply a lightweight RL agent on top of it. And temporal generalization, temporal inconsistency are some of the other problems we also face. And let us talk about the specific metrics. And these are the reference metrics that we are being using for, like, we can use these are the full reference metrics, and they can be used when we have a paired data sets. And peak signal to noise ratio is primarily used to it compares pixel wise values in the image, and it gives us a value in decibels. The higher the PSNR, the lower is the noise present in the image, and basically a higher PSNR is desirable. And same is with SSIM, its value ranges from -1 to 1, and structure similarity, the best is 1, and that is what we want to have. And SSIM, in roughly we can say that it tries to understand perceptually how we can understand an image. It measures that. And where adaptive enhancement matters is these are some of the use cases that we have pointed out. For example, in autonomous driving, remote sensing, security surveillance, basically any scenario where we don't have the presence of paired data sets and we want something to work smoothly, this adaptive approach will be very useful. And let us look at the prototype which we built, where we implemented a generative adversarial network, specifically CycleGAN, and we added a light RL agent on top of it. We trained a CycleGAN model on our own on our own data set, and it was a combined data set of reside and other data sets. And on top of that, we introduced an RL agent, and basically the RL agent, it was a proximal policy approximation based. It was the framework for it, and the underlying feature for it was BM3D block matching and 3D denoising module was being used to actually carry out the changes in an RL module.
Siddharth,
And
a quick reminder, you will have to wrap up in next 1 minute because it's
yeah,
already time. Yes.
sure. And these are the images. This is like an output of our model. The top left image that we see is the hazy input that we have, and then the right image to it, the next image to it, right next to it, is the output of the GAN model, and from there in sequence are the images which are being generated by the RL module on top of it. And we can see that as we move forward, the model is able to make the image more smoother and reduce more noise. And this is reflected in our metrics as well. We see the PSNR shows a steady, consistent climb. This SIM false, but it is because of the inherent nature of this SIM metric. And we can add a side-by-side comparison, and hence we can show that a lightweight module can improve performance in an existing model without having to retrain and spend a lot of compute and resources onto retraining a model from scratch. And that's our paper. Any questions?
Yes, good work that you have performed. I just want to know what all the parameters that you have considered. Can you just repeat?
Ma'am, in this we are evaluating primarily on the basis of PSNR and SSIM, ma'am.
PSNR. So how you calculated PSNR?
PSNR, ma'am, like like we have functions for it in Python, and like we have two images, ma'am, like the ground truth and the our output. We give both the parts of these images, and it mathematically there's a formula for it, ma'am. Yes, ma'am.
Yeah,
Based on the
the formula is there, but what values you have inserted in those formulas?
ma'am, it is the mean squared error between the pixel values, ma'am, of the two
Pixel
images.
value,
Like
yeah. So
it's
pixel you considered, right?
yes, ma'am.
For the whole image?
For the whole image, we have considered SSM, ma'am. That will give a broader image from SSM point of view. It will give about how perceptually good the image is.
Okay, okay. Good. Thank you.
Okay, thank you so much, Siddharth, for your presentation. So, our next speaker is Anthony Sebastian. Anthony, are you present in the meeting?
Yes, ma'am.
Yes. So he's here to speak on affordability barriers and adoption pathways, smart agriculture technologies for marginal farmers in Coimbatore district, Tamil Nadu. So yes, Anthony, you can start sharing your screen.
Am I audible?
Yes, you're audible.
Okay, just a second. And is my screen visible right now?
It is, yes, now it is visible. You can start.
Okay. So, good evening, everyone. My name is Anthony Sebastian, and I'm a Master of Social Work student from Amrita Vishwavidyapeetham, Coimbatore. And on behalf of my fellow researchers, I'll be presenting the paper on affordability barriers and adoption pathways, smart agriculture technologies for marginal farmers in Coimbatore district, Tamil Nadu. So before I start, I would like to thank the conference organizers for this opportunity. So, oh shoot, just a second. Is it moving? Okay. Okay. So this study explores why marginal farmers are still unable to adopt smart farming technologies despite their proven benefits. To say about the introduction, agriculture supports nearly 586 million people in India, and 86 are small or marginal farmers. Technologies like drones, IoT, AI, and automated irrigation can increase crop yields by 15 to 30%, while reducing water use by 30 to 40%. Yet, fewer than 15% of small farmers actually use these technologies. Most people believe farmers don't adopt technology because they lack money or are unwilling. However, our research argues that affordability is actually influenced by government policies, subsidy systems, institutional credit, and extension services rather than farmers' willingness alone. So because of these, we have concluded to three research questions. First, what financial and non-financial barriers prevent adoption? Second, what are the practical pathways through which marginal farmers adopt smart technologies? And finally, how can policies make these technologies affordable while remaining socially and environmentally sustainable? Our contribution is that we redefine affordability as a policy issue rather than an individual farmer problem. So this graph shows the approximate investment needed. It was a qualitative research, and we've interviewed three farmers who use different modes of technology for their agriculture. The first one used drip irrigation, which cost around 45,000 per acre, whereas solar irrigation costs about 2.5 lakh, and agricultural drone require nearly 6 to 7 lakhs. But the cost is only a single barrier. Farmers also face complex subsidy procedures, limited access to loans, inadequate extension support, and low digital literacy. Therefore, affordability is not just about price, it is about access. So we adopted a mixed methods approach. First, we reviewed more than 36 research studies, which was published between 2015 to 2026. We conducted detailed case studies of three marginal farmers in Coimbatore, and the data were collected through semi-structured interviews, field observations, and document analysis, followed by thematic coding and cross-case comparison. So this is the profile of the three farmers which we interviewed. Let's name them Farmer A, B, and C. Farmer A adopted multiple technologies, including drones and drip irrigation, using the Agricultural Infrastructure Fund credit. Farmer B adopted only drip irrigation using personal savings, whereas Farmer C independently invested in a solar-powered farming system without external financial support. These three farmers clearly represent three different adoption pathways, showing that there is no single route to smart farming. And the comparative analysis. Comparing these farmers revealed interesting differences. Farmer A relied on institutional credit and formal training. Farmer B depended on peer learning and gradual adoption. Farmer C learned independently through self-exploration. However, one finding was common among them. None of the three farmers successfully accessed government subsidies, even though subsidy schemes were still available. So, moving on to the key message of the paper, our findings highlight five important points. First, adoption remains below 15% despite clear productivity benefits. Second, farmers follow three distinct adoption pathways. Third, government subsidies are difficult to access, forcing farmers to depend on savings or institutional credit. Fourth, farmers themselves suggested practical solutions such as tiered subsidies, lower interest loans, equipment rental services, group purchasing, and free training. And finally, technologies must match local farming conditions. For example, drones are not economical for very small farms, while solar panels are less effective during rainy conditions. And based on the policy implications which could be possible, based on these findings, we recommend four policy interventions. First, introduce tiered subsidies based on the landholding sizes of the farmers. Second, automatically link subsidy approval with low interest agricultural credit. Third, encourage cooperative ownership and rental models for expensive technologies such as drones. And finally, strengthen agriculture extension services through digital advisory systems and farmer training programs. So to conclude, our research shows that smart farming technologies are not beyond the reach of marginal farmers. The real challenge is not the willingness of farmers, but the affordability ecosystem created by policy and institutions. With better subsidies, easier credit, stronger technical support, and cooperative models, smart agriculture can become both affordable and sustainable. So that's it. Thank you. To end it with a single line, Our study shifts the discussion from farmers who cannot afford technology, but it is shifted to our policies must make technology affordable. So thank you and welcome to questions. These are the references, by the way. Hello, ma'am.
Kirti ma'am, do you have any questions for him?
Yes, what is the size of data set that you have used?
3, ma'am.
Only 3.
Yeah, 3 farmers.
I thought it should be like at least because while listening the presentation, I heard 3 farmers. You were just
Yeah.
observed. Okay. Take it, no issues. Thank you.
Thank you so much, ma'am.
Okay, thank you so much, Anthony, for presenting.
Okay.
Yes, so our next presenter is K. Deepshik. Are you present in the meeting, Deepshik?
Yes, ma'am, I'm available.
Yes, so he's
Before
going to
starting
talk
my
about
presentation,
his uh, he
okay.
is here to present his work titled as Beyond Accuracy, Robust and Explainable Performance Evaluation of Intrusion Detection Systems for Internet of Things Networks. So you can start sharing your screen.
So actually, my camera isn't working. I'm facing issue. I'll directly share you the screen and start my
Yes, sure,
presentation.
sure. Yes, that is totally fine.
1 second. Is it visible, ma'am?
Yes, it is visible. You can start.
Yeah. Okay. Good afternoon, everyone. My name is Deepshik, and I'm studying at CMI College of Engineering and Technology from Hyderabad, Telangana. And my co-authors are L. Chandrasekhar Reddy. He's an professor, and other co-authors are G. Pranay and E. Deepak. Today, I'm going to present about my project titled Beyond Accuracy, Robust and Explainable Performance of Evaluation of Intrusion Detection Systems for Internet of Things Networks. These are the contents I'm presenting today. Introduction. So, the Internet of Things or IoT refers to the smart devices that communicate with each other throughout the internet. So these devices are used in many areas like healthcare, transportation, smart cities, industries, factories, like many areas. So as the number of connected devices increases, the risk or cyber attacks also increase. So to protect these networks, IDS systems called as intrusion detection systems are used. However, most existing IDS models are tested only on static data sets, which is not accurate in real time. And it may not perform well in real world situations where network traffic keeps changing. Therefore, our research evaluates the IDS not only based on the accuracy, but also on its adaptability, how robust it is, and how much explainability it gives. So, for example, let's imagine there is a hospital where all medical devices are connected to the internet. So, if a cyber attack occurs, the IDS must detect it immediately. But the existing IDS are old, all technologies trained only on old data, which might miss new attacks. So, our research evaluates how reliable and explainable an IDS in real world IoT environments. So, coming to the problem statement. Most IDS systems are designed to achieve very high accuracy on static datasets. However, in real-world IoT environment, network traffic continuously changes, and the attackers use many new techniques to attack. So, as a result, a model which performs well during the testing may fail after the deployment. In addition, many IDS models basically work like black box, and many IDS models are faces difficulty in security analysis for understanding what's the cause or etc. So therefore, there is need for an evaluation framework that measures not only accuracy but also its adaptability robustness. So yeah, coming to the objectives, the main objective of our research is to evaluate the performance of IDS beyond just accuracy. So we aim to analyze how IDS performs when the traffic, that is network traffic changes over time through concept drift analysis. And we also test its robustness against uh, many other detection techniques methods. In addition, we also evaluate the model on different IoT datasets to measure its generalization capability. And at the end, we use SAP explainability to make the model's decision more transparent so that it would be easier for security analysts to understand. And yeah, coming to the literature survey, we have gone through many papers, and yeah, these 5 papers, actually 4 papers, are from past 4 years. So what we studied with these research papers on idea systems are that most of these previous works only focused on improving accuracy using ML models, deep learning models, and some also focused on explainability. However, there they face some issues. So while others address concept drift, most of these studies evaluated their models only on static data set, and it did not provide a complete evaluation of robustness and explainability together. So to overcome these limitations, me along with my teammates, we worked on unified evaluation framework that combines drift analysis, adversarial robustness testing, and cross dataset evaluation. So yeah, this is our framework. Basically, our proposed framework starts by collecting the IoT network traffic from 2 datasets. First one is the TAN IoT and second one is the bot IoT. These datasets consist of 75 CSV files, which is up to, I mean, it has many features, labels like DDoS attacks, etc. So the data is then pre-processed by handling missing values and encoding the features, categorical features, and normalizing the data. We then train a multi-layer perceptron neural network, and after training, the model is evaluated with a concept drift, adversarial attack, and then cross dataset evaluation. At the end, sharp explainability is applied to understand the model's decisions. So this complete framework helps to evaluate the ideas based on robustness, adaptability, and explainability rather than accuracy alone. So this is the model architecture. Our IDS system is based on multi-layer perceptron, also called as MLP neural network. So this model consists of 3 layers: input layer, 3 hidden layers, and the output layer. The hidden layers use ReLU functions, that is activation function, to learn complex patterns from various network traffic. And dropout added to reduce overfitting while training or any other process, and to improve the model's ability to generalize the unseen data. And then in the output, we have used the softmax function to detect or to classify the traffic as either it's normal or malicious. And we have also used Adam optimizer along with the categorical cross entropy loss function to optimize the mode. And the method evaluation of methodology consists of 3 evaluation techniques. So yeah, our evaluation framework consists of 3 evaluations, as I said. First, we perform concept drift analysis using sliding window technique and adaptive window to check whether the model's performance changes as network traffic evolves over time. And the second one, we evaluate adversarial robustness using FGSM and PGD attacks to determine how well the model can resist malicious attacks. Finally, we used sharp explainability to identify the most important features, infine the model's predictions, and provide analyst or friendly response mapping. Together, all these 3 evaluations helps us to assess the ideas based on robustness, explainability, adaptability, rather than relying only on accuracy. And these are the experimental results. First one is model performance. So the proposed model achieved, initially achieved the accuracy of 97.47% on the 10 IoT dataset. We then evaluated the model with using concept drift, and as also we can see that in the left side graph, we can also observe that this left side graph represents the window-wise accuracy of IDS systems. As we can see, almost all window sizes accuracies are between 99.9% to 100%. So the Adwin algorithm did not detect any concept drift. This indicates that network remained stable during the evaluation period. So, and the right side graph, which shows the model's performance on the other dataset called as BOT IoT dataset. Even though the model was trained on ton, we are testing it using cross dataset, that is ton. And here the x-axis represents the sequential BOT IoT files arranged in temporal order, and the y-axis represents the model's accuracy. So by this overall, we can say that these two graphs demonstrate that the proposed IDS performs consistently over time. This indicates that model is stable and adaptable under different network conditions. And the second one is adversarial robustness. We have evaluated the robustness of our model against adversarial attacks using the method called FGSM. As shown in the figure, the model accuracy decreased according to the intensity is increased. The accuracy dropped from 97% to 38%, which is drastic change at the highest level. So, and the right side figure also clearly illustrates that even a small change in the input can significantly reduce the model's values. And these both graphs shows that model performs well under normal conditions. Its accuracy significantly decreases when there is an adversarial attack which is introduced. So this demonstrates that high accuracy alone does not guarantee explainability or robustness. So what we did is then we have used the method called SHAP for explaining the to check the results are transparent or not. So we perform explainability analysis using SHAP, which stands for Shapley Additive Explanations. These helps us to understand why the model did those predictions, a particular prediction by showing the contribution of each features. So in our results, there is source port and destination port were identified as the most influential features affecting the model's decision. This improves the transparency and helps the security analysts better to understand better and to gain the trust on IDS systems. And by this, I want to conclude that, in conclusion, we propose a robust and explainable evaluation framework for IDS in IoT networks. So instead of focusing only on accuracy, we also should be concentrate on other factors too. So we evaluated the model using the analysis method called concept drift and adversarial robustness testing, and the explainability analysis is done by SHAP. Although the model achieved an initial accuracy of 97.47%, after the adversarial training or testing, it showed that the performance could significantly decrease with small changes or under attacks. So therefore, our framework provides a more practical way or I would say trustworthy approach for evaluating IDS in real-time environment. And coming to the future work, we are planning to incorporate online techniques, which can be done or online learning techniques, so that the model can continuously adapt and observe or monitor the continuous changing network traffic. And we also aim to strengthen the adversarial defense mechanism to evaluate graph-based and hybrid intrusion detection models. And additionally, we will test this framework on large real-time IoT datasets. Actually, the one which we have used is already it's the size of 1 GB. But when we'll work with real-time, it might be of huge size. So yeah, we'll also work on it, and we further trying to improve the explainability using aligning sharp explanations. And if possible, we'll also use other explanation explainability techniques like line if possible. Yeah, thank you. Do you have any queries, please?
Okay, anyone have any questions? Kirti ma'am, anything to say?
Yes, the question is regarding the hidden layers. You have used three hidden layers. So why
Yes,
three?
ma'am.
What is so
I mean, like
special?
a neural network consists of three hidden layers, no, ma'am. I mean, like we give input, these hidden layers process the input data. Why we use three layers is to understand the patterns, relationships, and how these attacks are classified. So we use three hidden
Only
layers
three are
because
enough?
yes, ma'am. For classification, it if we increase the layers, we can get more details, but it takes a lot of effort and time, ma'am.
Okay, okay,
A neural network with three layers is enough to work on the real time data, ma'am.
okay, okay.
Thank you.
Okay, thank you, Deepshik, for presenting. So,
Yes, ma'am.
our next presenter is G. Chaitanya Shravanti. She is here to present her paper titled as Bidirectional LSTM based Early Warning System for At-Risk Student Identification in Programming Education. So, are you present in the meeting, Shravanti? Or any of her co-authors is present on behalf of her? Okay, I think she's absent. So let's move forward with the next one. So next we have Sejal Rupraj Bhagat. Sejal, are you present?
Yes, ma'am.
Yes. So she is going to talk about her work titled as Cybersecurity Solutions for Wireless Body Area Networks in Smart Healthcare Environments. So Sejal, you can start sharing your screen. You can start, Sejal.
Good afternoon, everyone. My co-author Supriya Narad and I, Sejal Rukraj Bhagat from School of Allied Science, to present our research paper, Cybersecurity Solution for Wireless Body Area Network in Smart Healthcare Environment. As a smart healthcare rapidly integrate into modern medicine, protecting vital patients' data has become a critical frontline challenge. Today, we will discuss how our proposed architecture address this challenge efficiently. Uh, Outline of presentation to we will begin with the background and introduction of a wireless body area network, followed by a review of a recent literature. We will then highlight the critical gap and a problem in existing approaches that motivated this work. Next, we will introduce our proposed three-layer hybrid cyber security architecture and system methodology. Finally, we will share our competitive evaluation results, explore real-world smart healthcare application scenarios, and conclude with the future scope of our work. Let's look at what wireless body area network or VWAN actually are. VWAN are network of low power variable or implementable sensor that collect a special real-time physiological data such as heart rate, glucose level, body temperature, and ECG. Why VWAN matter? Why does this matter so much right now? According to the World Health Organization, disease remain the leading cause of death globally with a protected 23.3 million dead by 2030. Concurrently, over 246 million people are living with diabetes. VBAN offer a revolutionary solution by enabling continuous remote monitoring without demanding request hospital visit, utilizing a combination of IoT, mobile ADHOC network, and wireless sensor networks. The security challenge, however, this brings us to a massive security challenge. These medical sensors are strictly resource constrained. They have very limited battery power, CPU cycle, and memory. Traditional heavy cryptographic protocols simply drain them too quickly. It's because this sensitive protected health information is sent completely wirelessly. It is highly vulnerable to malicious event dropping, replay attack, and man in the middle intervention. A literature review to contextualize our approach, we carefully review key security advancements over the last few years. In 2019, Su et al. Applied machine learning for anomaly detection to find malicious network nodes. In 2020, Raza et al. Designed a hybrid AES and ECC scheme to protect variable data with lower latency. La et al. In 2021 introduced to lightweight framework focus entirely on energy efficient encryption. Moving closer to the present, Kumar and Lee in 2022 explored automatic device pairing using unique ECG signal biometrics, while Rahman et al. In 2023 used blockchain for data traceability. Most recently, in 2024, Singh et al. Utilize federated learning to preserve privacy during collaborative model training. Despite this breakthrough, a glaring research gap remains in existing architecture, combined data encryption, instruction detection, and compressive key management into one single cohesive framework specifically optimized for VBAN. This brings us to core issues plugging current deployment. We have identified five main limitation: high energy consumption, traditional cipher like standard AES, RSA, or SHA are too heavy for microscopic low power nodes. Second, weak instruction detection. Popular routing protocol like Leech and HITS are strictly designed for energy routing efficiency. They feature zero built in a mechanism to recognize active network attacks. Third, isolated solution. Existing system address only a single piece of the puzzles, either encryption or authentication or anomaly detection, but never all three simultaneously. No real-time local decision making. Rarely strictly on the cloud falls.
Sejal, sorry to interrupt. a quick reminder that you will have to wrap up within next 1 to 2 minutes, as we are time bounded.
Yes, ma'am. Unacceptable latency during sudden medical emergencies. Privacy and compliance gap. Many model lack end-to-end auditability required by stringent framework like IPS and GDPR. To overcome this hurdle, we propose a three-layer hybrid security framework that balance robust safely with maximum resource efficiency. Layer 1 is the sensor layer consistency of the variable and implementable biometric device. This communicate via low power standard like Zigbee or Blue using a lightweight authenticate encryption with associated data or head. Layer 2 is the edge layer which shift the computational burden onto a local gateway, such as a smartphone. This gateway run a detected machine learning based instruction detection system to flag thread instantly without waiting for cloud processing. Cloud or server layer handling long-term secure storage, providing role-based access control by a BAC, and utilize a permissioned blockchain for a complete tamper-proof audit trail. By utilizing selective encryption, encrypting only the most virtual high sensitivity data field and integrating NFC or human body communication for secure out of band device pairing, we protect data integrity while existing battery lifespans. Methodology and system to our implementation focus on system device, structuring the precise topology for
Sejal, are you moving your slides because the movement is not visible on the screen? Are you able to hear me, Sejal?
yes, ma'am.
Your movement is not visible. Are you? If you're changing the slides, the movement is not visible. And now it is visible. You can just change the slides while you're talking. So yes, and wrap up within next 1 minute. You can continue, Sejal.
Yes, ma'am. Methodology and system device focus on system device, structuring the precise topology from sensor node to the edge gateway and up to the backend server. Handle data collection, simply gathering a continuous physiological telemetry like blood pressure, SpO2, and glucose. Phase 3 is algorithm development, where we deploy the head and key derivation firmware directly onto the sensor controller alongside
Sejal,
the.
actually we are time bounded, and what you are doing is you are just reading the slides. So, if you can explain it the whole paper in like a summary. Uh, you don't need to just read the slides. So, Kirti ma'am, you can ask questions.
No, no, I don't have any question because I also read the slides. Just
Okay.
ask her to conclude.
Okay, Sejal, you can just move forward to the conclusion.
Okay. So, in conclusion, research demonstrate that a layered hybrid framework combining lightweight cryptography, edge computing, machine learning, and automated key management provide comprehensive protection for medical IoT. Moving analyze to the edge effectively deliver real-time security with low power consumption and ultra low latency. Looking forward, our future scope include upgrading our edge system to a deep learning model for a protective prevention, integrating post-quantum cryptography to safeguard patients' data against tomorrow computing threats, and refining decentralized cross-device standardization for universal medical interoperability. Thank you, ma'am.
Okay, thank you so much, Sejal. So, Kirti ma'am, should we move on to the next presentation?
Yes, yes.
Okay. So, our next presenter is Athira P, who is here to present her work titled as Enhancing Sustainability Transparency Through Augmented Reality, the Impact on Consumer Trust and Green Purchase Intention in the Organic Food Industry. So, Athira, are you present?
Yes, ma'am, I'm present.
Yes, you can start with the
Uh,
presentation.
Ma'am, is my screen
Yes, it
visible?
is visible. Remember, you have to
Good
wrap up in 9 to 10 minutes.
Okay, ma'am.
Yeah.
So good evening, everyone. It's a great pleasure to be here today. So before I begin, I would like to introduce our research team. I'm Adira P, and I'm joined by my fellow researchers, Nikita and Varlakshmi. So on behalf of we are from Amruta School of Business, Kochi. And on behalf of our team, I'm delighted to present our research title, Enhancing Sustainability Transparency Through Augmented Reality, the impact on consumer trust and green purchase intention in the organic food industry. So coming to the introduction, we are living in a time when sustainability has become more than just a term. So it has become a way of life. So more and more consumers are choosing organic products because they care more about their health, food safety, and the environment. So however, while the demand for organic product is also increasing, the consumers actually doubt. Many products carry labels like organic, natural, or eco-friendly, but consumers often don't know whether these claims are genuine or not. So as a result, they rely more on brand reputation than on verified information. So at the same time, most exciting research has focused on using augmented reality to make shopping more engaging. But very little attention has been given to how AR can build trust and influence consumers' buying decisions. So this gap inspired our research. So the problem statements that we have focused is that the main problem we identified is that unclear eco labels and increasing greenwashing are reducing consumer trust in organic products. Although augmented reality has the potential to provide clear and interactive sustainability information, its impact on trust and purchase intention has not been explored in depth. So therefore, our study had five objectives. So first one is to understand whether AR improves consumer trust, to examine whether trust influences green purchase intention, to study the direct relationship between AR and purchase intention, to understand the mediating role of consumer trust, and finally to provide practical recommendation for organic food marketers. So we have conducted few literature reviews. So our literature review brought together three important areas of research. The first area mainly focused on augmented reality, where previous studies found that AR makes shopping more interactive, simplifies product information, and reduces consumers' uncertainty. The second area was sustainability communication. Earlier, research showed that eco labels are useful, but they are often confusing while greenwashing continues to damage consumer confidence. And the third area focused on was consumer trust. Researchers constantly found that the trust is one of the strongest factors influencing green purchase decisions. So, however, no study combined all these three areas: AR, sustainability, transparency, and consumer trust, specifically in the organic food industry. So, this is a unique contribution to our research also. So, coming to the research methodology, to address this gap, we have adopted a qualitative research approach. So, instead of conducting surveys, we analyzed real online consumer reviews from e-commerce platforms and organic food websites. And we also selected reviews that discussed sustainability, transparency, and trust, and while excluding reviews that focus only on taste or unrelated factors. So, to analyze the data, we used thematic analysis, which helped us identify meaningful patterns in consumer perceptions. Coming to the findings of the research, our analysis resulted in five key themes. First one is consumers appreciate clear and transparent sustainability information. Second, skepticism still exists because of misleading environmental claims. Third is that trust is built when consumers can verify clarification certifications and trace the product's journey rather than simply relying on advertisements. Fourth one is that greater trust leads to greater confidence in purchasing organic products, even when they are more expensive. And finally, environmentally conscious consumers respond much more positively to transparent sustainability information than consumers who are mainly price driven. Overall, our findings suggest a simple flow. Greater transparency reduces skepticism, builds trust, and ultimately encourages green purchase intentions. Coming to the discussions and implications, one of the most important insights from our study is that traditional labels often overwhelm consumers with limited or confusing information. Augmented reality changes this experience completely. By simply scanning a QR code, consumers can access detailed information about certifications, farming practices, supply chains, and environmental impacts in the interactive way. So this shifts sustainability communication from simply making claims to actually providing proofs. So for the businesses and policy makers, this means that technologies such as AR combined with blockchain and digital verification systems can significantly improve transparency, rebuild consumers' confidence, and support responsible consumptions. So coming to the conclusion of this research, this shows that the augmented reality is not just an innovative technology, it is a powerful tool for promoting sustainability transparency. So by making sustainability information clear, interactive, and verifiable, AR helps rebuild consumer trust and encourage green purchase intention. As consumers become more conscious of their purchase decisions, transparency will become just as important as the product itself. So I would like to end this with a note that is the future of sustainability marketing is not about making bigger environmental claims. It is about making those claims transparent, trustworthy, and easy to verify. Thank you all for the valuable time and attention. And we have also included key references from which we have taken. Thank you.
Okay, thank you so much, Athira. Kirti ma'am, any questions?
No question. Actually, I got disconnected in between.
Oh,
So,
okay.
no question for it. Yes.
Okay.
Okay, ma'am.
So,
Thank you.
thank you, Athira. So, for our next presentation, we have Koneti Manoj to present his paper titled as HATCOM, a self-supervised framework for community detection in heterogeneous attributed temporal networks. So, Manoj, are you present?
Yes, am I audible?
Yes, you're audible. You can start your presentation.
Yeah, may I please know if my screen is visible?
Wait 1 second. Now it is visible. You can
Uh,
begin.
okay. Good evening, everyone. Firstly, thank you so much for this opportunity. I'm Koniti Manoj. Today, I'm going to present our research work titled HATCOM, a self-supervised framework for community detection in heterogeneous attributed temporal networks. This work is carried out by our team consisting of Balaji, myself, Kartikeya, Ganga, under the guidance of our guide Dipti LR ma'am. We are from Amrita Kshetrapitam, Amrita University. So this is overall overview of what I'm going to cover in the further minutes in the presentation. I will be briefly covering the problem statement and our proposed framework, followed by system architecture, implementation, and finally conclusion and future work. And coming to introduction of our research, basically what is computer detection? Committee detection is nothing but it is identifying process of identifying of groups of closely connecting nodes within network. Basically, where it plays major role in applications such as recommendation system in social networks, where we get like recommendations based on the community we live in. Example, let's say Facebook or Instagram, we get our feed and reels based on the community or the state you live in. Example, when we live in Maharashtra, we tend to get more of Marathi content like in that way. The main problem is that in modern real world networks, they are much more complex than traditional graphs. They contain multiple node types, different relationships, also involving temporal interactions and rich semantic attributes. The problem is existing model often fail to capture all these characteristics simultaneously, which motivated us to develop a unified solution. So to put everything in some words, here is our problem statement. The problem statement is that the modern recommendation and social network contain heterogeneous node, evolving temporal interactions, and multiple relation types and rich attributes. Most existing community detection techniques either ignore temporal evolution or require manually designed metapaths or fail to preserve long-term behavior consistency. So these are the objectives of our project, like construct the graph, next use. So I'll be covering these objectives in depth in the coming slides. So coming to the proposed solution, to address all the limitations which I mentioned previously, we propose HATCOM, which is a self-supervised framework for community detection. The framework majorly introduced three major innovations. Firstly, the RTCA or the relation time coordination module, which captures both the relation semantics and the temporal recency during the message aggregation. The second one is the GTN or the graph transfer network, which automatically discovers useful metapaths without manual engineering. The third one is EMA based exponential moving average based temporal memory module. This module preserves the historical information and also stabilizes node embeddings over the time. So since our framework uses supervised learning, it does not require any of the labeled committed data sets. So here is our overall HATCOM framework overview. We are jointly modifying three main aspects, which are the heterogeneous graph structures, relation semantics, and temporal evolution. These three components work together to learn meaningful node embeddings, which we further then use for community detection and downstream evaluation tasks. So here is our overall system architecture. The workflow begins by constructing a heterogeneous graph from the movie lens dataset. The graph we further process by the RTCA module, which assigns attention based on the both relation type and timestamp. The resulting embeddings then we pass to the GTN module to learn higher order semantic structures automatically. Next, the EMA module, which stabilizes these embeddings across temporal snapshots. Next, we have this learned representation, which we use for community detection and evaluation. So these are the main algorithms which we are using in this entire process. First is the RTCL layer and the GTN layer. And main key features implement, as I mentioned previously, we first construct the graph, which consists of the users, movies, and genre. Then RTCA is applied for relation-aware temporal learning. Then the GTN module learns semantic relationships across multiple node types. Finally, the EMA module, which is the memory module, ensures the temporal consistency, while self-supervised evaluation pipeline is assessed clustering quality and link prediction performance. So coming to the results and performance here from the graph, we can clearly see that all the movies are all the movie embeddings are clearly grouped, and the communities exhibit strong structural coherence. In addition, we have also have the EMA memory model significantly improve temporal stability across graph structures. Overall, the learned embeddings are also like not only structurally but also semantically consistent. And here are the quantities, I mean quantitative results. We can see the modularity is 0.8579, which indicates highly strong communities, and the conductance is 0.064. Lower conductance means, which suggests that the opposite communities repel each other very strong, so the opposite communities are held far. And ROCAUC, you can see that 0.795, which means our link prediction is working pretty well. Also, the validation accuracy we are getting as 71.82, which also confirms that the embeddings are generalizing very well. Overall, these metrics demonstrate both structural quantity as well as predictive performance. For more further, we have also done the baseline comparison across different approaches like deep work, node to wake, and a simplified GTN model. We from the numbers, it is very clear that our HADCOM consistently achieved better results in terms of structural quality, stronger semantic representation, and more community formation. This improvement basically coming from the relation aware attention, automatic metapath learning, and temporal memory within a single unified framework. And we have also done ablation study, like we have, as I mentioned clearly, we have including all these modules, right? So ablation study is nothing but we remove one by one module and test how our module is performing very well. So our overall architecture is performing very well, as it is clear from the numbers we are getting. Removing memory mod, we removed the results. So at the end of the day, the results show that every component contributes that to the final model. Then coming to the conclusion, in the conclusion, I want to tell that our HATCOM provides a unified self-supervised framework for community detection in heterogeneous attributed temporal networks by integrating the RTCA, GTN, and EMA-based temporal memory. Our framework successfully models the heterogeneous structures, temporal dynamics, and relation semantics within the single architecture. Experimental results demonstrate improved community quality, stable embedding evaluation, and effective downstream performance. So finally, the future scope. In the future, we plan to extend the HATCOM in several directions. The other directions include scaling the framework to larger graphs, supporting real-life graph processing. Currently, we are taking an offline graph data, and we can also further apply this to other areas such as healthcare and cyber security. And we can also incorporate more advanced graph transform-based temporal learning mechanisms. So that's it from my side. Thank you. And any queries from us?
Yes, anything to say?
Yes, very good work that you have done. I just want to know, is there any hardware related dependency you have in your project?
No, no, ma'am, no, ma'am. All are software, all are deep learning model.
Hello?
No, ma'am, no, ma'am. Am I audible?
Yes, yes, yes.
No, no hardware we have used.
Okay. So
Yes.
I thought it is heterogeneous network, so maybe some hardware dependency may be there. But as you are saying, it is not there. Good work that you have done. You can just explore this work ahead with your like future directions, whatever you have mentioned. Try to implement that because it is promising work.
Okay, ma'am. Thank you so much. Your feedback means a lot.
Yes, yes. Okay, thank you.
Thank you.
Okay, thank you, Manoj.
Yeah.
So, moving on to the next presentation, we have Arnav Panikkar to present his paper titled as Prompt CV, a framework for reproducible and cost-aware prompt selection in large language models. So, Arnav, are you ready with the presentation?
Hello, hi. Yes, am I
Hi.
audible?
Yes, you're audible.
1 second, just sharing my window. Yeah, is it visible?
The presentation is not visible, the screen is shared. So when you click on share, after that you have to click on the presentation window and not the entire screen.
I am not getting this. Give me 1 second. I'm not getting this option.
When you click on share, there are
Just getting
multiple
this.
options you get.
Is this visible? Um,
Okay, what you can do is you can resolve the issue and then we will come back to you after
okay,
another presentation. Yes.
okay.
Yeah. Okay, so next we have Mridul Dinesh to present his paper titled as VANET-based intelligent traffic signal for congestion control and emergency vehicle prioritization. So Mridul, are you present?
Yeah, I'm present.
Yes, you can start.
Okay, yeah, sure. Is my slide visible?
1 second. Yes, it is visible.
Okay, yeah. Good evening to everyone present here. I'm Mridul from PS University, and I'll be presenting a project which me and my teammates Naresh, Tarun, and my guide Dr. Shantamina S worked on. And before I start, I'd like to thank the organizers and the panel present here and everyone else to give me time to present my project. Okay, so the title is VANET-based intelligent traffic signal for congestion control and emergency vehicle prioritization. So I'll be going through the introduction as to why we picked this as a project, problem statement, and then the methodology, algorithms, and so on and so forth. I wouldn't want to waste time speaking about this. And then, so introduction. First, when we started with this project, we knew we wanted to work with vehicle ad hoc networks and communication between vehicles. So we had actually gone through three verticals, which was traffic management, intelligent routing, and resource scheduling. Literature survey was done on all three of these. And finally, we decided to use traffic management with emergency vehicle prioritization as our problem. And why so is it's pretty evident, right? Emergency vehicles need to make through the signal at the quickest, and it's noticed that they don't get through as quick as they can. And fixed time signals obviously lack adaptability. Now, the question arises that India has already moved past fixed time signals. They are vehicle actuated control signals throughout the country. But the issue, the novelty which we wanted to bring in was those are dependent on pressure sensors and cameras. Now, pressure sensors are always prone to wear and tear, and cameras wouldn't work as well in weather conditions such as rain, fog, and snow. So, what our plan for the project was to detect approaching emergency vehicles using the VANET communication, and whatever system we come up with should be independent of any hardware which can get affected due to the weather conditions, and there should be communication between the vehicles and infrastructure. And we decided to go ahead with reinforcement learning and to be more specific Q learning because of the ever changing nature of how traffic signal is. There are n number of variations which can come up in traffic signals. And and the end goal is to reduce congestion while maintaining smooth traffic flow for all vehicles. So yeah, that's the problem statement. Methodology, it was an all software implementation which we did, and there are basically two parts of this project. One would be the network communication, and the other would be the implementation of the Q learning algorithm on the traffic as it is. So we've used true softwares for this. We've used Sumo for the simulation of the traffic signal, which we have incorporated with Vanes for with using Vanes with Omnet for the network communication. And yeah, So as you can see the diagram here, Sumo has the simulation going on in it, which is in tandem with Omnet, and they store the communication logs. And the communication delay is passed on to the Q learning model, which in turn gives the decisions back to the simulation. This will be more clear as I move forward with the presentation. Okay, so now this is the communication aspect of the project. If we wanted to implement a VANET communication in the future, one major issue is that the latency shouldn't be high. There shouldn't be too many unwanted messages, and there should be no redundant transmissions. So for that, we had to come up with an algorithm to make sure only the required messages are being passed on. So we came up with the counter-based rebroadcast, in which the emergency vehicle broadcasts this message. The neighbors receive it and start passing it on to the further neighbors. However, to reduce the redundant neighbors, each vehicle would have a counter which would stop rebroadcasting once it has received the message more than 3 times. So this reduces the number of redundant the transmissions happening. Also, to be noted that this would require an onboard unit with the vehicles, which we are considering as it is there, as we are doing only the software implementation of this. And the further things what we have done is we wanted to incorporate an RSU next to the traffic signal so that there can be communication between the signals as well. So for our project, we have worked on multi-signal, that is two signals, and the message should pass through from one signal to the other. So for the RSU polling mechanisms, the RSU is constantly checking for emergency vehicle messages which receives, and if it does receive it, it starts polling a message to all the required edges in the sense the other directions which the vehicle can go, informing them that an emergency vehicle is on the way. And other than that, we have also done route-based filtering, whereas the RSU sends the message only to the path the emergency vehicle intends to go in. So in the message which is sent by the emergency vehicle, the route is mentioned. So the filtering is done at the RSU accordingly and passed on to the remaining vehicles in the required path. So yeah, this was the communication aspect of the project. And talking about the data generation, so the agent was trained using a replay buffer, and we'd use 200 simulation episodes. And yeah, these were the cases which were done, which is low density. There's a directional imbalance where one direction gets more flow, and then high density congestion, then extreme EV frequency pressure, and heavy arterial corridor flow. Now, the Q learning part of the project. So the controller acts as the Q learning agent interacting with the environment at 1 second intervals. And the basic philosophy is that the emergency vehicle's time to arrival is directly enforced into the reinforcement learning state space. I'll be getting into that further. So as you can see, the state space and action. Yeah, so state paired consists of EID and QID, which is EID is for which edge the vehicle is in, and Q length is for the length of the queue the vehicle is in at the current position, and P current is the current position of the EV. And this is the formula which we have used for the time to arrival, which is the length of the lane minus the current position of the lane divided by the max of which are either 1 millimeters per second or the speed of the EV at the moment. And match is to check if the EV is already in its intended path and it's a green light situation. Now, action space. There are three major action spaces which take place, that is, extend, switch, and emergency override. When after the signal has completed, there will be a 5 second time for to prevent premature switching, after which the switch takes place. And again, the switch stays for a minimum of 10 seconds. So that's 10 plus 5, 15. So emergency override is on a case when the time to arrival is lesser than 15 seconds, in which case whatever the signal is automatically gets overridden for a green signal. So these were the action space. And here is the reward function which we have used. So it consists of R weight, which is the total waiting time divided by the total vehicles, and this is penalized by minus 0.2. Then R pressure, this penalizes if there are more vehicles coming in, less going out, but at the same time rewards if more are going out and less are coming in. And there's throughput. And we've also done based on the speed of the EV. If the EV is moving at less than 2 meters per second, it is penalized. But at the same time, if it moves at zero point 0.7 of its maximum speed, it is rewarded. And here are the results from the counter-based rebroadcast. We have done a comparison with a simple flooding, that is, there is no suppression of messages. And from the graph and the table, it is evident. So the red depicts the simple flooding, where there's no algorithm applied. It has an exponential rise in messages sent, whereas at the same time, the counter-based rebroadcast is much more linear, the blue line. And yeah, that and then the results of the emergency vehicle performance. So we had done for 34 vehicles had passed through the signal, and a regular fixed time signal with no algorithm took 76.48 of an average delay, whereas a 30-second interval had 35.05 seconds interval, whereas our algorithm had 9.01 second as the delay. And this is also to show how the reward changes based on the speed ratio. The speed ratio is the current speed of the EV by the maximum speed of the EV. So when the vehicle is critically stopped, it gets a heavy penalty, a lesser penalty when it's on a slow crawl, and a moderate penalty when it's on a moderate speed. And when it's flowing well, it's rewarded. So that's about it as what we implemented. So we had implemented a VANET-based reinforcement learning traffic signal controller, and it had multi-case reward functions. And for the communication aspect, we had enforced the counter-based rebroadcast to reduce the number of redundant messages. Yeah, that's about it. Thank you. Is there any questions?
Uh, so you got very good accuracy and the results are also good. So any that assumptions you have made while doing testing?
Yeah, the main observations we made were the reward functions and how they change is what we made out. And another aspect which we were looking into but didn't get into was how we could incorporate collisions in the middle of the thing, because that's a new scenario, right? But we didn't get to it. So that was another thing we were looking into.
Okay, thank you.
Thank you.
Okay, thank you so much, Mridul, for your presentation. So, Arnav, are you ready with the issue resolved? Yes, so you can start.
Yes. Okay, so my
Yes.
screen's visible, right? One
Yes.
sec. Okay. Hi everyone. I am Arnav Panikar and I am presenting this in behalf of my team. We are students and our teacher, Dr. Veena Karani. We are from Computer Engineering Department of DJ Sangvi, Mumbai. So Prompt CV is basically a framework for reproducible and cost-aware prompt selection in LLMs. Basically, it's a framework that treats prompt design as a hyperparameter selection problem. Okay, so if two prompts produce different results, which one should we report? In most of the LLM papers that we see nowadays, the prompt choice is informal. It is selected ad hoc. There's no standardized way of understanding how it has been selected. A handful of phrasings are tried hand by hand, and the best one is kept. So yeah. So why prompt selection is unreliable today? We have manual trial and error. A few phrasings are tried by hand and the best performing ones are kept. There is currently no selection protocol. Run to run variance changes. There's a hidden inference cost. Okay. So the prior work we're comparing it to the prior work. So based on prompt engineering and instruction design, you had the chain of thought and the manual tuning, but there's no standardized selection procedure. You have automatic prompt optimization techniques like the automatic prompt engineer, which optimizes prompts, but you don't have variance or cost-aware reporting. You have got programming frameworks like DSPY, but there is no, standardization of selecting from a small grid. So each of these 6 research threads solves one piece of the puzzle only. None of them combine the structured selection, variance awareness, and cost-aware reporting into one protocol. And that is the gap that we are filling with Prompt CV. So yeah, these are our 3 main contributions. Firstly, we have a structured prompt search. You have got a hyperparameterized grid. We have variance-aware evaluation and cost-aware reporting. So our framework has the 4 following steps. One is we split the data into a selection set and an evaluation set, after which we go ahead with the prompt generation. Then we have the repeated evaluation where each config is run k times under fixed decoding. By fixed decoding, I mean like the temperature is fixed, top P, frequency, penalty, these are all are fixed. The reason why we decided to go with fixed decoding is that even if the score comes different for every run, we understand that it's because of the prompt and not because of the decoding structure. And that is why we have kept that constant. And after that, we are able to get the logs and the rankings. Okay, so we have got total 5 parameters in our framework. One is there are 3 different kinds of roles, expert, tutor, neutral. For instruction style, you can either have concise or detailed. For reasoning, you have none, implicit or chain of thought. The output format can either be in free text or JSON. And the shots is, we have got few shot and zero shot, like 0, 1, 3, and 5. We have a basic template in which we basically put in these values. There are a total of 144 theoretical combinations that are possible. We prune this to 100. The reason being is because it is computationally expensive. And we do this by using a staged protocol where we have got 3 stages. One is a screening, one's a mid, and one's full. And after that, the top 100 configurations basically survive. And yeah, that's how we get the final 100. This is the basic algorithm that we had come up with. First, the data set is split into a selection set and an evaluation set. Then for each prompt configuration that is in our hyperparameter grid, we we do the trial and sample shots and then run the model on our evaluation data set, after which we evaluate the metric scores, the variance, the cost variance, and the adjusted score. The adjusted score is what we get from the mean score divided by the cost into latency. Okay, so for the data sets, we used a total of 6 data sets. We used 3 different kinds of data sets. In classification, we used the SST2 and the IMDb data set. And our main metric that we were focusing on here was accuracy and the macro F1 score. For the question and answering data sets, we used the squad and the trivia QA, where we used normalized exact match and character match as our metrics for LLM outputs. And the final one is structured output, where we use the Wiki SQL and the E2E NLG data set. And the metrics we use the JSON validity and the field match. In all of these data sets, we use the 60 to 40 split, where 60% was the selection set and 40% was the evaluation set. Like I mentioned earlier, we are using the fixed decoding policy here. We use temperature to be 0.2, top P as 1. Yeah, so now when we compared it to zero shot and our few shot performances, we saw that few shot improved 5 out of the 6 data sets. Only SST2 was the only exception, and that is because SST2 is a simple binary sentiment task, and the model had phrasing bias or label bias that pulls the model away from the direct instruction. Now coming on to the variance and stability across our trials. As we can see, there was no variance for the squad and the E2E NLG dataset. The highest variance was reported for the SST2 and the Trivia QA dataset. The highest accuracy scores was present for the SST2 and the IMDb dataset. Yet, when we look at the cost-aware evaluation, that is another thing that we are bringing in, is the IMDb dataset, even though it had a mean score of 0.940, it used around 605 tokens, which is almost 9x what we got with the SST2 dataset, which had a mean score of a 0.9. So after we use the adjusted formula, we get an adjusted score of 0.0569 for the SST2, which massively outperforms the IMDb's despite its higher accuracy. So basically, we are also taking into account the number of tokens, the cost that's spent on generating these outputs. So our key findings from this paper was that there's no universal winner. 5 times we had the few shot winning, and once we had the 0 shot. So yeah, variance definitely matters. Like I mentioned, the SST2 and the Trivia QA had a lot of variability. So, and because of that, the mean score can mislead. The cost isn't proportional to quality like we saw in the IMDb scores case. So when it comes to the limitations, there's a finite prompt grid. Transferability depends on dataset choice. There are exhaustive grids. Strict JSON-only constraints may affect behavior. Single fixed decoding policy. One of our future work that we plan is basically combining the joint prompt and the decoding sweep. Also, wider range of prompt variants and model families, robustness analysis across different decoder settings, deployment-focused cost metrics, that's throughput and monetary cost as well. Yeah, that's about it. So a prompt selection should be evaluated like a model hyperparameter on a held out dataset across repeated trials and with cost reported alongside performance. Thank you. I'm ready for questions.
Okay, Kirti ma'am, any questions for him?
What is the data size that you have used?
Most of these data set sizes were around 5 to 6 million. Yeah, we used total 6 data sets, and we have evaluated on each data set separately.
And how many from the data set you have used as training data set?
60%, 60-40 was the split.
60-40. Okay. Thank you. Yeah.
Thank you.
Okay, thank you so much, everyone. So this was the last presentation for today. And as we have come to the end of this session, I sincerely thank all our authors for their excellent presentations and valuable contributions, and all the participants for being an important part of this international conference. I truly hope that this session was very insightful and engaging for everyone. On behalf of the entire team, we thank you all for your continued support, not just for this edition, but for all the previous editions of this conference. We look forward to welcoming you again in the next version, 2027, as well. All presenters will be receiving their digital certificates through their emails within 2 working days, and the publication will be getting live within 7 to 8 months. So we kindly request your cooperation with our team. And I would also like to extend my sincere thanks to our session chair, Dr. Kirti Vanjhale ma'am for expertly chairing this session. And this is a small token of appreciation on behalf of the team ICT4SD 2026 and Global Knowledge Research Foundation and partners. So thank you, Kirti ma'am, for joining us. And thank you all once again for your valuable presence. So before we officially wrap up, let's capture this as a memory. So I kindly request everyone to please switch on your cameras for a group snapshot. So please everyone
Excuse
turn
me,
on
ma'am.
your cam.
Excuse me, ma'am.
Yes, Deepshik.
Ma'am, actually, my friend Chaitanya is not able to attend the presentation.
Yes.
So, is there any possibility to reschedule it? I have completed with mine, but she has also need to give the presentation, but at the moment she can't give it seems. Is there any possibility to reschedule?
We will let you know that.
Sure,
Okay.
we will let you know via email. You
Yeah.
can just raise the email, your query regarding that. So we will answer you that on the email. Okay?
Okay, I'll tell her to raise the. Thank you, sir.
Sure.
Yeah. Thank you so much, everyone. Thank you. Take care. Stay safe, everyone.